Hi, I'm Matthew from Topology Teaching, and welcome to this video on what topology is, why we have chosen it as an exemplar topic for pure maths communication, and what areas of topology we have focused on. Topology is the study of invariant properties of mathematical objects which remain constant when we manipulate them. Topology is a notoriously complex area of maths, usually only taught at upper undergraduate level. However, it's a highly visual topic, so can be taught in an accessible and engaging fashion, and has much potential for displaying pure university maths to a wider audience. The field started with Euler, who noticed that for all polyhedra, 3D shapes with flat polygonal faces, the number of vertices minus the number of edges plus the number of faces is 2. This sum, called Euler's characteristic, is an example of a topologically invariant property, which remains the same when we deform shapes into each other. From the observation of Euler, we can conclude that any polyhedron can be moulded into another. This idea can be further generalized to the curved surface of a sphere. We can draw a point on the surface of a sphere and an edge around its circumference. If we define the number of faces as the number of disconnected surfaces generated by cutting along all edges, we generate a system with one vertex, one edge and two faces, giving an Euler's characteristic of 2, showing any polyhedron could be deformed into a sphere. Topology is a fascinating field because it features in a variety of key mathematical areas with links to science and the wider world. The ideas of Euler outlined before can be translated to graph theory, a branch of maths which deals with networks of nodes connected by edges to form graphs. Any connected graph, such that a path can be drawn between any two nodes, which is planar, so is drawn without any edges overlapping, has an Euler's characteristic of 2. In this case, we consider nodes as vertices and the number of faces as the number of regions enclosed by edges, plus 1 for the infinite region outside the graph. It seems too much of a coincidence for polyhedra and such graphs to have this identical property, and it is. These objects, despite originating from seemingly unrelated areas of maths, are connected by the fact that if we project any polyhedron onto a 2D plane, we obtain a connected planar graph. The topology of such graphs can in turn be applied to the study of molecules. Analysing graph representations of molecules by examining their connectivity can allow us to predict the relative boiling points of different isomers, molecules composed of the same set of atoms with different bonding patterns. This has direct application to designing fractional distillation systems to separate the different hydrocarbons present in crude oil. We can take this idea of Euler's characteristic even further by considering vector fields. Vector fields arise when we assign the value of a vector quantity with magnitude and direction, such as velocity, at each point in space. The most intuitive example is a vector field representing the direction and speed of fluid flow. A classic case of this is weather forecasts, which depict a wind velocity field using arrows in space, the orientation and length of which represent the speed and direction of airflow. When we consider vector fields on a surface, as with weather forecasts on the Earth's surface, Euler's characteristic for this surface defines the minimum number of singularities in the field, points in the field around which vectors point in completely different directions. These singularities are classed by the vector field's behaviour around them, including sources, net outward flow, sinks, net inward flow, vortices, net rotational flow, and others. Given the fact Euler's characteristic for a sphere is 2, we can conclude that at least 2 singularities exist in the Earth's wind velocity field, showing that it is impossible for the wind to be blowing in one direction everywhere on Earth. Singularities in the wind velocity field manifest as rotational weather systems we know as cyclones. Thus, topology links geometry to graph theory to vector fields through the central unifying concept of Euler's characteristic. In this way, topology draws connections between diverse fields of maths. Finally, we can take the ideas of topology and apply them to knots, objects formed by twisting the ends of a string around each other and fusing them to form a closed curve, and links, sets of one or more intersecting knots. These objects are visualized by projecting them onto a 2D plane as a knot diagram, with crossing points represented by breaks in the underlying curve. Knots and links have invariant properties which remain constant irrespective of the angle from which you project them onto the page. One such property for links is the linking number, informally the number of times 2 closed curves wind around each other. This property remains invariant for DNA, which consists of 2 helical strands with regularly spaced base pairs bridging them, winding around a central axis. DNA has a linking number of 1 per 10.5 base pairs. This remains constant, irrespective of how DNA is structured, whether it be a linear chain or itself coiled for storage. Overall, topology provides us with a framework to use visual and vibrant ideas to explain areas of maths and apply them directly to the real world. Thus, it has the ability to captivate and show how pure maths is used throughout science and society.